Okay, so next session is dosimetry for next generation. And I'm a co-chair of this session. My name is Tatsuhiko Sato from Japan Atomic Energy Agency. It's a member of the Committee 2 and the 2 task group in ICRP. Okay.
Hello, good morning, everybody. I'm the other co-chair. My name is François Bochu. In my day-to-day life, I'm a professor of medical physics at Lausanne University in Switzerland. I'm also a member of ICRU, but the real reason why I'm here is because I'm the chair of C2, which is dedicated to dosimetry. And as you saw in the previous session, the title was Going Beyond Dose. So that means that dose is not that important in a way. That was maybe the hidden message. Actually, we'd like to show you that dose still matters. Also, we are all aware that dose is clearly not the only parameters to be taken into account in radiological protection. But anyway, it is important to realize that it is often the first quantity that we want to know. In most radiological protection circumstances, we want to know the dose. In other words, the dose sets the scene, and it is a quantity that needs to be considered as a fact, and it has to be trusted by all stakeholders, I'm sure. And in this session, the presentation will show the efforts that are done within the ICRP, and in particular in C2, to have a solid dosimetry that is accepted by everybody. The presentation will also show how dosimetry makes it best to respond to the present and future challenges in order to keep the system fit for its purpose, as you all know the motto. And we wanted to be able to propose an applicable solution in practice, and it is important according to our present state of scientific knowledge. So this session will be organized in the same way as the previous one. We will start by make a summary of the multiple posters that were submitted for this session. You'll have more information just afterward. And actually, I'm glad to say that Camille Pacher will actually make a summary and present some hint of what was actually submitted in this session. So Camille, you have the floor.
All right, I'll get straight into it. I don't want to take up too much time with this, but it is important to, at least for you to get an idea that there were, for this session, a huge number of submissions. Overall, there were 249 posters and 83 pre-recorded videos that were submitted for this symposium. There were more contributions from Asia and the Pacific than in previous symposia. So for this session specifically, initially we had something like over 60 posters and videos that were submitted. In the end, some were redirected to other sessions. In the end, the ones that are available online, we've got 28 posters that are available online and 8 videos. I've sort of divided them into general categories. 18 were medically related, 4 were industrial related, 12 technology, methodology, and then there were a couple that didn't fit anywhere in any of those 3 categories. In terms of themes, so I tried to look for certain themes. I highlighted those that I thought could be of specific interest. So fetal dosimetry, for instance, and pediatric, then modeling and simulation, occupational exposure, patient exposure, software, algorithm, application, app development. Then we have technique, methodology, and also stuff that had to, or posters that had to do specifically with dosimeters. In the fetal dosimetry, so obviously this is not going to be a review of all of those posters. I've highlighted for each of those categories some that were of interest, so I picked one amidst the category to give you an idea, but I highly encourage you to go check the posters and videos online. So for fetal dosimetry, there was a poster called a biokinetic model to assess radon uptake by the fetus in pregnant women. This was a Cousins Award finalist. It considers both inhalation and ingestion of radon and its impacts, and it relied on 2 ICRP publications, namely publication 88 and 137 part 3 in their dealings. And it considered both changes in maternal tissue and development of fetal issues. Now, in any of those summaries that I'm going to give you of the posters, I tried to stay away from giving away the punchlines because we do want to encourage you to go and read the posters for yourselves. It's more to pique your curiosity and encourage you to go and have a look at all of those. In the pediatric patient category, I selected enhanced radiation safety in pediatric chest CTs, assessing dose efficiency of automatic exposure control versus fixed tube current using CTDI vols, SSDE, and water equivalent SSDE. This looked at 179 pediatric patient CTs. Patients were 15 and under and divided into 4 age groups for the dealings and analysis. And the CT image dose report provided the CTDI vol and the DLPs that they used for the analysis. Yes, you can view the poster for more details and the conclusion. In the modeling and simulation category, I selected a video presentation by Philip van Havere. By when will computational dosimetry replace physical dosimetry? I thought this was quite interesting. He looks at advances in computational dosimetry, current issues with dosimeter wear, uncertainty of the results that we receive depending on how well people wear them, and so on. Then he imagines what the advantages could be if the doses could be calculated swiftly. He chose a RAF, so a flexible anthropomorphic phantom for the calculations, and then use Monte Carlo simulation. And he goes through a whole set of cases and examples. So basically, I think the presentation is about 20 minutes, and half of it is examples and cases, which I thought was really interesting because you get to see their calculations and their technology in application. So for example, they looked at interventional radiology, so you can follow where the doctor goes, then syringe and hand tracking for nuclear medicine applications, and then also he looks at the reactor sector. Anyway, very interesting talk. Then there's the occupational exposure category. So in there I selected occupational radiation exposure for industrial radiography in Saudi Arabia. This was a survey of doses from a total of approximately 100 industrial radiography and nuclear gauge facilities in Saudi Arabia. It covers a period of 5 years, and the dose results for 2,166 industrial radiation workers was analyzed, and they plan on using the results of the survey to improve practice and maintain their doses of LIRA. For patient exposure, I looked at optimization of patient doses in nuclear medicine, a pilot study. This was a retrospective study. It basically established DRLs for their most common procedures. There were approximately 30 patients per protocol. Some, they weren't able to get to 30, so their minimum was 10 patients. And they established their DRLs and compared the values that they obtained to values of other retrospective studies. For the software category, I looked at intercomparison of dose calculation software. So in this case, what they do is they compare 2 existing software, specifically those that are capable of integrating ICRP's latest updates. So they looked at Taurus and Myodose. They considered 2 scenarios for comparison and performed the calculation and compared the results. In the technique and methodology section, it was beyond GIAMSA, I'm not quite sure how to pronounce this, development of a simple high-speed C-banding staining method to improve identifying what was it again? Centromeres, I thought? No, anyway, sorry, the title's a little cut off here. And the objective of this poster the research was to improve identification of chromosomal aberrations in exposed persons to shorten delay between exposure and reporting of absorbed dose estimate. They developed a process that is speedier and focuses on accentuating centromeres. And at the end of the poster, they have two images comparing the different techniques and a quiz. So you can actually go scan the QR code and get the answer to the quiz. For the dosimeter category, there is bleaching mechanism of thermoluminescence signal in beryllium oxide dosimeters. The idea was to get a better understanding of the luminescence mechanism in beryllium oxide. They examined residual thermoluminescence glow curves after various bleaching times and compared thermoluminescence signal to optically stimulated luminescence signal. So that's really just a very, very brief overview. You can access all the posters and videos through the ICRP online poster platform. There is the link on page 5 of your symposium program. And the posters are available to attendees of the conference for the next 2 weeks following the conference. After that, it'll be open to the public. That's it. Thank you.
Thank you very much, Camille, for this very good overview. I hope that everybody wants to go and visit the posters during the week. And I encourage everybody to do it, obviously. So we can now start with the 4 presentations that we'll have this morning in this session. The first one will be given by Professor Yeon-Soo Yeom from Yonsei University in Korea. Yeon-Soo is actually a new member of C2. That's his first C2 reunion this year. But he is not new at ICRP because he already contributed quite a lot, in particular in the field of the mesh type reference phantoms. So if you have any point you'd like to know about these phantoms, Yeon-Soo is really the guy who can answer you. So Yeon-Soo, you have the floor.
Thank you, Chairman. Thank you for the great opportunity for me to introduce the mesh type reference computational phantoms for the general recommendation, which are developed by the ICRP task group 103. So this slide shows the current ICRP reference computational phantoms for adults and children. So these are voxel models based on the CT images and therefore anatomically much more realistic than the stylized phantoms. However, these voxel phantoms have some limitations due mainly to the voxel resolutions. So for example, the skin of the phantoms is not continuously represented because of the limited voxel resolution, which can induce an error in dosimetry. The same problem can be also found in the hollow organs, such as stomach, urinary bladder, and gallbladder. So going back to the skin, this is more problematic in dosimetry, especially the 50 micro thickness, the radiosensitive basal cell layer in the skin is considered as a target region for the skin dose. But this thin layer cannot be defined in the voxel phantoms. So therefore, the ICRP produce the reference skin dose coefficient using the simple the box model, not using the voxel phantom. Such limitation is relevant not only to the skin, but also to the 4 respiratory tract organs and the 7 alimentary tract organs. Even the range of the eyes directly exposed to air, this anatomical problem can result in significant overestimation in range dose calculation for weakly penetrating radiation. So therefore, to produce the range dose coefficient of the ICRP, the detailed eye model were separately created, but installed in the head of the stylized phantom, not voxel type reference phantoms. So consequently, ICRP currently use 13 additional stylized model for the adult only. So even when including children, about 50 stylized model additionally used in the current ICRP dosimetry system. So other limitations also listed here. So among them, I would like to stress that the current Voxel phantoms are matched to the reference value, but the reference values are exclusive of blood content. So that's why the organ mass is usually smaller by 3 to even 20%. So meanwhile, phantom technology in the world has been advanced toward the first generation of the computational phantoms based on tetrahedral mesh. So as you know, at the beginning, the human body is very simplified, such as box, cylinder, and sphere. We consider the first generation of the phantoms is stylized phantom, which first defined the individual organs using mathematical equation to make the organ-specific dosimetry possible. However, it is not so realistic. So from 1980s, the Voxel phantoms, like the current ICRP reference phantoms, are considered as the second generation of the computational phantoms. So Voxel phantoms are based on tomographic images of the human anatomy, and therefore much more realistic than the stylized phantoms. However, again, due to the limited resolution, the mostly millimeter scale used, the Voxel phantoms cannot precisely define the scene structure, such as the micron scale radiosensitive target lesion. And also, Voxel models are not really deformable and inevitably represent stair-step boundary. So from 2000s, the nervous or polygon mesh-based surface phantoms are considered as third generation of the computational phantoms. These surface phantoms show smooth surface, and also it's very flexible, so we can define very thin, small, and thin and small structures, and even highly deformable. However, the most existing surface phantoms need to be voxelized for Monte Carlo dose calculations. So this means it is going back to the Voxel phantoms. That's why losing the advantage of the surface phantoms. Of course, the recent the polygon mesh phantoms can be directly implemented for Monte Carlo code without any voxelization. However, the computation speed is extremely slow when compared to the Voxel phantoms in general. And also, sub-organ density variation cannot be described in the surface phantoms. So now I would like to stress the first generation of the computational phantoms, based on tetrahedral mesh. So tetrahedral mesh is constructed by filling the tetrahedrons fully inside the volume of the polygon mesh, which is called tetrahedralization. So therefore, we can fully maintain all the advantages of the surface phantoms. Moreover, the tetrahedral mesh phantoms can dramatically accelerate the Monte Carlo the calculation speed over the polygon mesh phantom, even faster than Voxel phantoms for some cases. In addition, the sub-organ density variation also can be defined in the mesh phantoms. So this is the summary of the phantoms and showing the superiority of the tetrahedral mesh compared to the previous Voxel and nervous or polygon mesh. So acknowledging the limitation of the aforementioned, the limitation of the Voxel phantoms, and at the same time, the cutting edge, the phantom technology, based on the tetrahedral mesh. So ICRP Committee 2 in 2013, the meeting decided to convert the Voxel Phantom into high-quality tetrahedral mesh format. The new reference phantoms will replace the current Voxel Phantoms from the next general recommendation. So to implement the project, the task group 103 was established in 2016. So this is the initial membership of the task group. So this task group includes worldwide experts in the computational phantom and the dosimetry field. So for example, as you know, as you can see, we work together with Dr. Maria Janker and Dr. Nina Petrosy-Hans, who developed adult Voxel-type reference phantoms. And also we work together with Dr. Wesley Borch and Dr. Chun-Sing Lee, who developed pediatric Voxel-type reference phantom. So we all work together. So this is the current membership involving the much more experts now, as well as 5 mentees and the technical secretary involved in our task group. So this slide shows the adult and pediatric mesh-type reference phantoms. Adult phantoms were already released with ICRP publication 145 in 2020. And pediatric phantom will be released very soon with ICRP publication 156, which is now in press. The skin of the 1-year and adult male mesh phantoms and are shown as an example. So you can see the micron-thick, the radio-sensitive basal cell layer in the skin are well defined in the phantom. And moreover, the micron-thick radio-sensitive target region, as well as very thin micron-scale, the source region in the alimentary tract organs and respiratory tract organs are well defined in the phantoms. And even very complex long airways are also comprehensively defined, modeled in the mesh phantoms. And also the mesh phantom include very detailed eye model, and also the detailed teeth model, which can support the EPR dosimetry. So this slide shows the rotational view of the adult and pediatric, the mesh-type reference phantoms. So dosimetry impact of the mesh phantom on effective dose calculation is generally small for external exposure to photons and neutrons. However, the significant impact can be observed for electron as well as other charged particles at certain energy region, which can establish steep dose gradient within the skin. Therefore, the dose to the skin target region in the mesh phantom are significantly different from the dose to the entire region, skin region in the Voxel phantoms. Significant impact for the internal dosimetry can be also found for some electron crossfire irradiation cases. For example, when the lung is the source and red bone marrow is the target, the SAF values of the meshed phantoms are significantly lower due to the improvement of the skeletal system in the mesh phantoms. The Voxel phantom do not fully include the spongiosal region, including RBM, by very thin but highly dense cortical bone. And very recently, our task group just completed the development of the pregnant female and fetus mesh-type reference phantoms for the 8 gestational weeks. So this slide shows the maternal phantoms and the fetal phantoms. So to know more detailed information on the pregnant female mesh phantom, please check the poster number 2008 in this symposium. And lastly, I'd like to briefly introduce some works done for the mesh phantom extensions and applications. So due to the high deformability of the mesh geometry, so we deformed the mesh phantom into the 5 different postures, so working, sitting, bending, kneeling, and squatting. We also deformed the phantoms into different body size, even more extension to the library for 108 males and 104 female phantoms. And all phantom in the library were also deformed to make the arms raise up for the medical applications. We also created a pediatric phantom library for 331 males and 281 females. I think these phantom libraries will be useful in many applications, and also in the new ICRP task group 128 about individualization and stratification in the radiological protection. We are also developing an independent GUI-based the Monte Carlo program in order to easily and simply calculate organ dose using the mesh phantom for the external exposure. So this program is called MAXI. So this MAXI will be used also to calculate reference dose coefficient for external exposures in the emergency situations by task group 112. So I'd like to show some demonstration of those reconstruction for the accident using the MAXI. So this animation shows how the MAXI works. Users can easily define the geometry and the phantom for Monte Carlo dose calculation without any knowledge on the phantom and Monte Carlo code. So this is the summary of my presentation. Thank you very much.
Thank you, Yansu, for your very clear and didactic presentation. As I said, we will keep all the questions at the end. So the next presenter is actually my co-chair, Tatsu Sato. He's a member of C2, but now he's not speaking as a member of C2 because he's also a member of a task group of the ICRU, our sister organization. And he will talk about a new report that is about to be published on microdosimetry. So Tatsu, you have the floor.
Thank you for introduction. Okay, so today's my talk consists of following 4 topics. And I would like to start with the introduction of ICRU itself and microdosimetry. So, as most of you know, so ICRU, International Commission on Radiation Units and Measurement, established during the first International Congress of Radiology in London in 1925. And currently 15 commissioners, including our chair, Francis, who are experts in radiation oncology, radiology, medical physics, nuclear medicine, and radiation protection, are working for this institute. And so far, ICRU published 97 reports, including the ICRU report 36, published in 1983, entitled Microdosimetry. So it has been past 40 years since the last publication on microdosimetry by ICRU. So we think that it's a good timing to update and publish a new one. And the report will be ICRU 98. So next, I would like to ask you about the general questions about microdosimetry. So does microdosimetry simply represent the dosimetry with small size target? So let's think about these questions. So maybe you can get to the answer why I ask these questions. So as you guess, my answer, of course it depends on person, but my answer is no. Small size target is a necessary condition, but does not sufficiently explain the feature of the microdosimetry. So the next question is, what happens when the target size becomes smaller? So it also has several answers, but my answer I would like to introduce here is the fluctuation of energy imparted in each target become large. So this picture is a famous picture taken from Rossi paper in 1968. And absorbed dose become fluctuate with a decrease of mass. Where is the pointer? Sorry. And turned into a stochastic quantity named specific energy in microdosimetry. So the last question is why the fluctuation of energy imparted is important. My answer here is it changes the biological effect even when the mean dose is same. So let's assume the situation that 4 cells has 2 grades equal 2 grades, or 1 cell has 8 grade and 3 other cells has 0 grade. So heterogeneous case. Both cases, the mean dose are the same, but you can easily imagine that their biological effect, such as survival fraction, different. So microdosimetry implies the microscopic dosimetry that considers the stochastic nature of radiation interaction. So next, I would like to introduce our new ICRU report on microdosimetry. The title of the report is, as I said before, the stochastic nature is the key words of the microdosimetry. So the title is Stochastic Nature of Radiation Interaction, Microdosimetry. And these are the author of the report, and chaired by Les Blavy, who is the author of previous microdosimetry reports. So he has been working for microdosimetry over 5 decades. And the last 2 authors are Maria Branton and Pavel Ork, commission sponsors. Here is the table of contents of the report. So first section is introductions, and third section is for definition and theory. Fourth and fifth sections are instruction for computation. 6 to 8 are for instruction for measurement, and 9 are for the applications, and 10 is the recommendations. So it covers all topics related to microdosimetry, and it has over 300 pages. So actually it's huge ICRU report. So of course I cannot introduce every contents here. So I would like to introduce some recommendation we wrote in our report. The first one I would like to introduce here is a borderline between microdosimetry and dosimetry, conventional dosimetry. So I think almost all of you agree that the DNA is a target for microdosimetry or even nanodosimetry. But how about a cell with the size of tens of microns? Some of you think it's a target of microdosimetry, but some of you are not. So to answer this question clearly, we write the recommendation that when the mean number of charged particles, including delta I, originated outside the site, interacting with the volume of interest is small, the stochastic nature of radiation interaction should be considered. Such a situation will arise when the reciprocal of the particle fluence is comparable to or larger than the cross-sectional area of the volume of interest. In the mixed radiation field, the fluence of higher LET components should be considered. So let's assume the same target size, left and right side, the same target side. But the fluence, the left-hand side is a lower fluence case, and right-hand side is a higher fluence case. And the color indicates the specific energy of each target. And if the fluence is low, then those become heterogeneous, and microdosimetry consideration is necessary. But right-hand side, when the particle fluence is higher, the dose is homogeneous, so conventional dosimetry is sufficient. So not only the target size, but also the particle fluence or type of radiations can determine whether the stochastic nature become important or not. Actually, this recommendation is rather common sense to researchers working on microdosimetry, but it has been never documented explicitly. The second recommendation is a clarification of the definition of linear energy Y. Linear energy is defined as the quantity of energy imparted and the mean code length. But it is not clear that the code length represents randomly generated or particle path lengths inside the target. They are the same for spherical target case, but they are different for non-spherical target case, such as cylinder. And it is almost impossible to construct a spherical shape detector, so experimentalists generally use the particle path length, mean cone length, because then Y can be correlated with LET. But it's not documented. So we explicitly write that when evaluating linear energy in a non-spherical detector by a non-isotropic radiation, the mean cone length, which the best approximates the mean of charged particle path length in the volume of interest, should be used. But this is rather minor clarifications, and no dramatic change in the definitions of the microdosimetric quantity is proposed in our report. So next, I would like to talk about the role of the microdosimetry in the past and future radiological protection system. So this part is my personal opinion and not written in the report, so please be careful. It's my opinion. I think there are two major application fields of microdosimetry. One is medical physics for charged particle therapy, and the other is space dosimetry. For example, microdosimetry-based biological models are used in the treatment planning of carbon ion therapy, and gas field and solid-state microdosimetry detector are used for beam assurance. And for space dosimetry, astronauts' risk due to the cosmic ray exposure are estimated using the quality factor proposed by NASA, considering the track structure effect, and gas field detectors are used for characterizing the cosmic ray environment in spacecraft. And the keywords are high LET radiations and relative biological effectiveness, RB. So, suggesting that microdosimetry is useful in the RB estimation. So, let's think what is the ongoing topic related to RB for preparing new ICRP recommendations. So, I ICRU report. So we must remember that ICRU report 95, entitled Operational Quantity for External Radiation Exposure, jointly published with ICRP in 2020, says that the limits to prevent the damage of eye lens of eye and local skin should be set in the absorbed dose rather than equivalent dose, because WR used in the calculation of equivalent dose relate to stochastic effect rather than tissue reactions. And RB weighting of absorbed dose in relation to specific health effect could be applied for the protection and operational quantity as appropriate. However, RBE for preventing tissue reactions has not been proposed either ICRP or ICRU. So including this issue, ICRP recently launched a new task group entitled RBE Quality Factor and Radiation Weighting Factor. And the objective of this task group is to review the determination of RBE and especially derivative value of Q and WR, and provides the support or even lack of support for particular values, models, and determination that influence radiological protections. And the proposed approach for modification in this value will be considered. So, how did microdosimetry contribute to the determination of the Q and WR value? So I'm a member of this task group, so I would like to introduce some review of this determination. So, quality factor was first introduced in ICRP-ICRU joint report as a discrete function of LET, and revised in ICRP 26 as a continuous function of LET, so-called QL, as shown in the left graph, and revised in its form in the ICRP 60. However, no biological background was provided for these revisions. On the other hand, WR was introduced in ICRP 60 as a discrete function of particle type and energy, and revised in ICRP 103 as a continuous function of energy to be numerically consistent with QL in ICRP 60. So, just reviewing this official history, microdosimetry seems to have no relationship with this determination. But in 1986, microdosimetry-based quality factor was defined in ICRU 40 as a continuous function of linear energy, QY, mostly based on the experimental data or RB data of dicentric chromosome production of human lymphocyte. And if I plot the data, assuming that Y equal to LET, we can see the overlap between QY and QL defined in ICRP 60. Considering that the QY is older than QL, it could be the origin of the QL, and that means origin of the current WR. So, we can say that the microdosimetry contribute to the determination of quality factor and WR, and then it has the potential to contribute the proposal of new quality factor for preventing tissue reaction. So I would like to talk on this topic on Thursday. So let me summarize my talk. So ICRU will publish a new report on microdosimetry in the near future, currently in press stage, so hopefully early next year. And the new report covers all topics related to microdosimetry, including definition, theory, computation, measurements, and applications. And microdosimetry has contributed to establishing the current radiological protection system, particularly for determining Q and WR, and will continue to contribute to the new ICRP recommendation. Thank you very much for attention.
Thank you, Tatsu. I'm sure that this somehow mysterious field of microdosimetry is now clearer for most of you, because clearly I really enjoyed your talk. So thank you. It's a difficult subject, and I think you managed to present it in a clear way. So that means that I can give you the floor now with a new hat, the one of co-chair.
Okay. Okay, so next talk will be provided by Alexander Ranovsky, also a C2 member. His title is Next ICRP Recommendations, Dosimetry for Animals and Planets, Time for Probabilistic Paradigms. Okay, please.
Paradigm. Thank you, Chair. Dear colleagues, as already announced, we would be looking now to the dosimetry aspects for the environmental protection. And that's why just a few words that what we should consider for environmental dosimetry relevant for the improvement of the new ICRP recommendations, which are expected or planned to appear in 2030s, in considering all aspects of radiological protection, including environmental radiological protection and dosimetry, which also will be in the focus of this activity. To deal with this, we have to ask questions and answer them. Does the current ICRP dosimetric framework for non-human organisms fit the purpose? And is it time to think on modifications and improvement? And also the interesting question to answer is, do the single value fixed dose estimates work well for animals and plants, given their extreme environmental diversity and biota-specific radiological protection endpoints? So another question would be helpful to think about is it already time arrived for the probabilistic paradigm in the environmental dosimetry? Few words about the current system of ICRP for environmental radiological protection. It was mostly grown on the outcomes of the European supported projects FACET and ERICA, and outlined in the series of the ICRP publications, of which publication 108 and 136 delivered those coefficients for the non-human organisms. Current ICRP methodology for dosimetry of animals and plants was introduced in the publication 108, updated in 136, and both publications were printed with the tables of those coefficients for reference animals and plants for a limited set of radionuclides. Therefore, publication 136 was complemented by the online tool to allow the flexible calculation of the dose coefficients for all radionuclides considered now by ICRP. In 2021, the well-known assessment tool, ERICA tool, was made fully compatible to these ICRP recommendations in the part related to dosimetry calculations. And recently, publication 148 delivered recommended values for the radiation weighting factors. So what are the main principles of the current dosimetry for non-human biota? We are dealing with the extreme diversity and variety of living organisms regarding their sizes, shapes, masses, composition of bodies, biology, biokinetic lifestyles, and environment. So for this, we need to use different methods to cope, to address this situation. First of all, we formulate those coefficients for a set of reference models called as a reference animals and plants. We use conventional dosimetry, unlike it was a previous speaker explaining us about the microdosimetry. Here we are firmly stay on the conventional dosimetry approach. As much as possible, we try to use superposition principle to model the complex situation using the combination of simple ones. We use simplified representation of irradiation geometry, body shape. And biokinetic for internal dosimetry is not accounted for. That's why uptake of radionuclides is described via lumped equilibrium concentration factors, CR. And of course, we use widely used uniformity assumptions, which is related to densities of the media, activity distributions. And as a tool, we also apply interpolation and where physically justified extrapolations, including allometric scaling. A few examples about the challenges which are now facing in the dosimetry for environmental protection. External dosimetry in forests. Its current dosimetry model for the terrestrial vegetation are very simple, derived for the open flat surface and the uniform infinite plane layers of biomass above the ground. Field studies, including those done in Fukushima prefecture, affected area, demonstrated as non-flat terrains, various types of vegetation, varying biomass density, non-uniform distributions of radionuclides, seasonal variations, varying locations of animals. To what extent these our current generic models, idealized models, applicable to the specific assessment tasks, it remains an open question. And that's why sensitivity of those coefficients to variability of environmental factors and locations of animals needs to be investigated using the field data. And of course, for these representative scenarios need to be formulated to allow for the radiological impact assessment in the forested environments. Another example of the challenge is the doses for the free-ranging animals. Studies for such animals wearing GPS-coupled dosimeters showed that the dose rates vary widely, and due to movement of the animals across non-uniformly contaminated natural or semi-natural areas. Estimates of external doses for animals based on the single measurements done at the trap site, either soil sample or ambient dose measurement, do not correlate with the actual dose rates experienced by animal. External doses estimated from mean soil contamination concentration were not conservative and under-predicted external dose to representative animals. So that means that for this situation, research needed to determine mean dose rates and variance for an animal or a group of animals and relate these effects to radiation exposure. Another challenging example is related to the freshwater environment, because current dosimetry models for aquatic biota formulated for infinite water medium, which is adequately applicable for the marine conditions or big lake situation. However, terrestrial freshwater bodies often very heterogeneous, finite in size, and aquatic organisms often found close to the interfaces to air or to sediment, and field studies in the Chernobyl exclusion zone demonstrated that the spatial variability and gradients of radioactive contamination on the ground surface and within a fresh water lake, where the substantial amount of radioactive material was found accumulated in sediment, all this created the strong gradients of external dose rates within the lake. So, whether the current ICRP approach can be applied in this situation or needs to be modified, it's currently under investigations and will be studied further. And another example is related to a problem of connected to sampling, monitoring, and dealing with the big arrays of data, big data. So it's well known that the successful environmental radiological assessment relies on sampling and monitoring data. So whether the available monitoring data represent the radiological situation is a question. To which extent and what are the uncertainties of the monitoring data and corresponding dose estimates? We already witnessed this example here in Japan, that a comprehensive monitoring network was created, including airborne, mobile, portable, stationary instruments, complemented by systematic sampling in the environment and laboratory measurements. So such a system was very effectively supplying significant data which were used, for example, in the recent UNSCARE report with the reassessment of the consequences of the Fukushima Daiichi nuclear power plant accident. So remote sensing and spatial analysis is applied currently in the Chernobyl exclusion zone to assess, for example, quality of forests. And this is also related to ecological services, and to quantify pertinent ecological and radiological parameters. This is an interesting study which shows that we can look closer at the emerging technologies like robotic instruments, automatic sensing equipment, satellite imagery, everything which results in collection of the big data and which probably would require the modern computerized methods of processing. So these technologies deliver us new opportunities, so we have to think and probably adapt our approaches to these conditions. So how could we improve dosimetry for environmental radiological protection? First of all, we need to find a reasonable and practice-justified balance between realistic and generic models, which are used to derive dose coefficients for the wildlife non-human biota. So we have to be able, we need to answer the questions. What exposure scenarios are relevant for the purposes of environmental protection? How much realism or specificity of the dosimetric model is enough? What are the uncertainties of the dosimetric model parameters and dose coefficients? And where do uncertainties in those estimates come from? For this, better understanding and quantification of associated uncertainties due to inherent variability of organisms, their habitats, and radioactive contamination, especially in the terrestrial environments, is required. So management of those and effects uncertainties can be facilitated by use of the novel approaches, for example, based on probabilistic techniques. IAEA currently runs the coordinated research project on external dosimetry for wildlife in the terrestrial environments. And this is activity which justified by the existing gaps in the current recommendations on dosimetry. And activity is aiming at the advancing dosimetry methods and data in the terrestrial environment for the non-human biota and to contribute to the novel techniques based on the probabilistic network. So another important part of this activity is a synergism with the ICRP Committee 2, which cooperates and advises to facilitate collection and production of the data and results which can be later used by ICRP to improving their recommendations. So for the future ICRP framework for environmental dosimetry, we can say that the main goal should be to provide relevant dosimetry data for assessment scenarios for wildlife representing variety of organisms, environments, and exposure situations. That means one has to define assessment scenario as a characterization of species, habitats, environments, behavior, sources of radiation exposure situations. Assessment scenario spans ranges of parameters regarding the masses, locations, and other details. So this needs to be defined using statistical language in terms of distributions or intervals. To implement a scenario-based assessment, grids of those coefficients are required, covering the ranges of the parameters variability. So this can be already compared to the previous talk on the human mesh phantoms with a family or hundreds of these phantoms developed to cover the variability of human. But again, this leads to appearance of the big data and related technological aspects. Those coefficient grids can be created using different modeling techniques, including Monte Carlo, analytical, numerical techniques, and so on. Those estimates for impact assessment need to be reported also as distributions, reflecting variability and quantifying uncertainties. So to conclude, I would just provide as a summary, say that those coefficients for specific irradiation situation and assessment scenario, these are two sides and key elements of environmental impact assessments, and both are important. Assessment scenario defines exposure and organism-specific parameters, which need to provide quantitative values characterizing the whole exposure situations. Here we see some opportunities for this talk and cooperation with colleagues from other task groups or from the Committee 4. Grids of dosimetric data matching the parameters domain are required. Here, it should be probably our task, and might be we have to think about the establishing the new task group to develop in this direction for the new term. Probabilistic techniques allow to merge the grids of dosimetric data with scenario-defined data, resulting in dose distributions for environmental entities. These dose distributions can be put into radiological protection context to support environmental radiological protection tasks and decision-making. This is probably a field where we should cooperate with the other committees like C1 and C4. So new emerging technologies for information collection, processing, and analysis require rethinking and possibly change of paradigm for the environmental radiological protection. And few words just to say a few names of colleagues to whom I would like to acknowledge, discussions with whom and their contribution and cooperation. And that's basically all of my talk. Thank you for your attention. And
thank you, Alexander. It's been a very much comprehensive talk on the environmental dosimetry. So as we said, so we will take the question at the QA session, and we would like to move the last talk of this session. Will be provided by Dr. Derek Jokis from the Francis Marion University in USA. He's also a member of the committee too, and his title is Specific Absorbed Fraction for Reference Individual for the Current and Next General Recommendation. So please start.
Thank you very much. So I have the highly coveted last talk before lunch, I believe. I will do my best to make it interesting. And with a topic like specific absorbed fractions, how can it not be interesting? So if I do my job today, I'm going to spend about half the time talking about a forthcoming publication of SAFs, aged and sex-dependent SAFs, that is really connected to the current system of radiation protection and the dosimetry supporting that. And then I'll spend about the other half of the talk talking about some improvements that I think could happen or perhaps should happen for internal dosimetry in the next set of recommendations. So first, just to make clear what we're talking about when we talk about a specific absorbed fraction. As you know, Committee 2 oversees the computation of internal dose coefficients. These coefficients give effective dose to a reference individual, which is actually redundant to say that, per activity of intake. And so what is the SAF and how does it contribute to the calculation? We've got to talk a little bit of maths here, though I am going to do it pretty quickly. In about a month, Task Group 95 is going to give a webinar on the first publication of internal dose coefficients to the public. And we'll go through this a bit more slowly as part of that webinar. But certainly if we're calculating effective dose, we need equivalent dose as an intermediate step. So equivalent dose rate is the product of two terms in internal dosimetry. What I call the source term, this is the term that comes from the biokinetic models. It basically gives the activity in source regions as a function of time. And then the S coefficient, which is the energy absorption or a physics term. And this gives the equivalent dose to a target per nuclear transformation that takes place in a source region. So the SAF sits inside that second term. So if we look at that and break it down, it's composed of all these fun symbols: the radiation weighting factor, the energy and yield of radiation emission from a radionuclide, and we have publication 107 to help us with that. And then that capital phi is the specific absorbed fraction. And that is a simple ratio of the absorbed fraction per mass of target tissue. So what's the absorbed fraction? This is the fraction of energy emitted from a source region which is absorbed into a target region. So if you look at that diagram, an example would be what fraction of energy emitted from the liver was absorbed in the heart, and we divide by the mass of the heart. So in the forthcoming publication, we have 79 source regions, and those are defined based on the biokinetic models that we have. We have 43 target regions. These help us get to effective dose, and then we have a few other things like lens of the eye that don't contribute to effective dose, but we're nonetheless interested. 6 ages, 2 sexes for each age. We have 4 radiation types, and then we have a grid of energies for electrons, photons, and alphas. So what that gives us is over 3 million individual SAF values. And they're all perfect. I'm glad you laughed. So here's the forthcoming publication, which I learned yesterday. This will be publication 155. On the right, I have, there are lots of publications that feed into publication 155, peer-reviewed publications, I should say. Here are 3 big ones dealing with the whole body voxel phantom transport for photons, electrons, and those spontaneous fission neutron emitters. So the big highlights, we're excited about this. We think it represents significant improvements to internal dosimetry for the ICRP. SAF values for male and female reference individuals at 6 different ages. This publication also has source and target masses for the reference individuals. That's really important. Inclusion of a whole body blood source for the first time. Publication 133 has these values for the adults, and we have not changed those, but we are providing them in publication 155 as well, so that a single download will give you everything. And then in addition to photons, we have energy-dependent SAFs for electrons and alphas, and that's a significant improvement over what's been done in the past. All right, so how do we compute these SAFs? The first big piece is we need to define our reference individuals, and there is no image of a reference individual. Reference individuals are not the same things as reference phantoms. Reference phantoms are very important to this process, but reference individuals are a much larger theoretical construction, right, that involves all kinds of parameters that are necessary to compute doses to the reference individual. So they're tables, right? Publication 89 is easily the source that has the most information about our reference individuals. We did need to supplement publication 89 to do this work. And there are several examples, but easily one of the biggest is we needed a distribution model for blood in different tissues in the body as a function of age. Publication 89 gives that data for the adult, but it didn't provide that data for younger ages. We need to know models of tissue geometries and their compositions. So this is where our phantoms come in, right? So the whole body phantoms, here we're using the voxel phantoms in publication 155. We also have image-based models like the skeleton, right? So again, voxel-based geometry, but based on an image of real human skeleton. And then we have mathematically defined stylized models. So in the gastrointestinal tract and the respiratory tract, we have mathematical models. The image here is an example of the stylized model we used in the small intestine, right, which allowed for some crossfire for electrons between different segments of the small intestine. And then we need models for radiation transport physics, right? We have these geometries, so now we've got to simulate radiation transport. Here are 4 examples. I won't tell you which one is my favorite, though I will tell you which one has my favorite logo. It's the one that has the Greek letter phi as the head of this adorable owl. I should totally turn that into an animated series, like, you know, this owl goes around the world teaching radiation physics. I would watch that. All right, where will the SAFs be used? So publication 133 SAFs have already been used in the OIR series, and there's the publications associated with those. The age-dependent SAFs will be obviously used in the internal dosimetry to members of the public, what we call the EIR series. The first part of that has already been out for public consultation and approved for public approved for publication. Task Group 36 is involved in preparing a report on radiation doses to patients in diagnostic nuclear medicine. They'll be using these SAFs. And then task group 112 is working on emergency dosimetry, and these SAFs will form the, will underlie the internal dosimetry associated with that report. So here's the one plot I'm going to show you of SAFs, right? So 3 million plus data points, and I'm showing you about 150 here. That's all you get to see. If I was to show you all of them, I think it would take 20,000 plots like this, which, who knows, maybe that's a future webinar, 20,000 SAF plots. Okay, so what's this one? This is inside the skeleton, and I've picked the 15-year-old female. And these are SAFs for different source regions inside the skeleton, all irradiating a common target, which is that bone endosteum. And the bone endosteum target has changed here. It is now 50 microns thick. We used to use a 10 micron definition. So that's a difference. What are the kinds of things that we looked for when we were checking this data, right? 3 million data points. We want to have some confidence that we've done this correctly. Well, all of those low energy values, right? This is for electrons, I should have said that. All the low energy values we can theoretically compute what those low energy values should be. So when we have data coming from a Monte Carlo code, we can check that low energy point to make sure that it's hitting the place it should. And then in this particular example, what happens at high energy, as your electron energy goes higher and higher, the source region becomes less and less important, right? So we see this convergence of them. And then finally, another nice feature with this model is that we're allowing for escape of energy from the skeleton to the surrounding tissues. So we see that decrease at the highest energies. Okay, so switching gears now. Improvements, possible improvements associated with the next recommendations. So first, do we need new targets, right? I talked about 43 targets that we already have, but maybe we need new targets, right? We're still learning about which tissues, cells, et cetera, are the most important for a particular biological response. And so if we have new targets, they may need new dosimetric models. A few examples. In the United States, NASA is very interested in possible response cognition as a result of exposure to high LET radiation. And so they actually got interested in alpha emitters and whether we could learn something from studying internally emitted alpha emitters in the brain. And so the NCRP's published a couple of reports, including new biokinetic modeling for subregions of the brain. And here's an example of how activity may not be uniform inside the brain. This is radium. And so if we were to ever implement a model like this, we would also need a dosimetry model for doing subregions of the brain and assigning dose to different regions. Circulatory system, right? Are we talking about circulatory disease? And if so, then what's the target? Is it the heart wall? Is it walls of the arteries? Kidneys? Central nervous system? Right? So these are all important questions that we'll need some answers to if we're going to model the dosimetry. And then an easier one is the urinary bladder. Keith Eckerman and Ken Vino have already published work that talks about subregions in the bladder and a target that's important. And if I'm correct, these are implemented in the mesh phantoms, correct? So that's an improvement that will be in place for the next system. So you've already heard about the mesh phantoms. I'm going to hit these very quickly, right? The alimentary tract will be a significant improvement. I'm particularly excited about the mouth here, the oral cavity. That's a significant improvement over what we have in some of the other, the existing models. The respiratory tract, and then the skeleton. And this is very cool for me to see high resolution spongiosa inside the whole body mesh phantom. Vasculature model. So I mentioned that we have a whole body blood source for the first time. Well, if we have alpha emitters in the blood, right now we treat organs as homogeneous mixtures of blood and parenchyma tissue. But for alphas, maybe we shouldn't be doing that. There should be some self-absorption taking place in the vasculature for alpha-emitting radionuclides in the blood. So this is interesting work out of the University of Florida, where they've modeled the vasculature inside the liver and looked at some of that self-absorption. So that could be a very interesting piece. Also could be a model for giving us dose to artery walls. Okay, and then I'm going to end with something that's not actually SAFs, and that's the biokinetic modeling. So I'm going to come back to this equation, and remember it was the product of two terms, right? And so those two terms should be consistent with one another. But right now our S coefficient has all kinds of sex dependency built into it, right? We've constructed all these nice phantoms with sex dependency. But our systemic biokinetic modeling does not have that sex specificity. We use one set of systemic biokinetic models and apply them to both males and females. And oftentimes, not always, but oftentimes, it's data for the males that is applied to the female. So my colleague Rich Leggett has done a little bit of a pilot study looking at the impact of what if we went to sex-specific biokinetic modeling, how would things change? And so he picked iron, and this is the biokinetic model for iron that you'll find in publication 134. And there are significant differences between males and females for how iron moves through the body. There are 5 storage compartments for iron. Iron, it turns out, right, our bodies do a very good job of recycling iron. We hold on to it. It's valuable to us. So it's what a biokinetic modeler would call a tight recycling model. And so those 5 storage compartments are very much involved in that. And then I've highlighted one other compartment down here, which is a transition from the red blood cells to other excreta. And this represents menses in premenopausal females. So in publication 134, what you will find is that this transition is there, but it is zeroed out. Okay? So this makes a big difference if you treat this in a sex-specific manner. So how big of a difference? Let's look at actual doses. So these are publication 134 dose coefficients to the red marrow, the liver, and kidneys. And you see the sex specificity there, the difference between the male and the female, but we are applying male biokinetics to the female here. And so the dose to the female targets are larger because of the sex specificity we have on the energy absorption side, the SAF. So what if we change that? What if we apply sex-specific parameters to the female now with everything except for the absorption from the gut? We're going to, for the moment, keep that constant for both. So this is just changing the parameters in those transitions, and you see the female doses drop. And that's because they're excreting iron faster than males do. Okay, this wouldn't be the right picture, but it gives you a sense of the impact of just changing those parameters. If we were to do this right, we need a sex-specific FA. Because females excrete iron at a faster rate, they absorb more of it from the gut. And so when you change and apply sex-specific FAs, the female value should be perhaps 0.15, the male value should be lower, 0.06, and you see male doses drop and female doses hop up. And yes, effective dose will change here. So I think this actually would be the single biggest improvement to internal dosimetry in the next system. All right, so to conclude, that pediatric SAF publications in press, the electronic download will accompany, it will have SAFs and source and target mass data, and they do represent significant improvements. Future improvements, I won't go through them all again. So with that, I will wrap up. Thank you very much.
5 minutes is fast. Thank you very much for interesting talk, and I look forward to your next webinar with explanation of 3 million data. Okay, so let's start the discussions, and maybe open for question to everybody. It's fine. So if you have any questions, please raise your hand and go to the microphone, or so please start.
So you divided the object into three of ages, 3 groups, or 6 groups, right?
You talk about SAF, so I'm sorry, it's confused. So this is a discussion for all talks, so please ask which talk you like to ask. So you talk about the last,
last
okay.
Right. And so what is the definition or discrimination of this age group? I wonder.
Yes, so very important when we define, which ages we're going to need for dosimetry to members of the public. What we look at are having enough information to do meaningful interpolation between those ages. And so this is why we have both a newborn and a 1-year-old, because of the rapid growth that's occurring in that first year, right? So we have a newborn, essentially a 0-day-old, a 1-year, a 5-year, 10, 15, and then the adult.
So if you apply to this to the other species, you should consider the age dependence differently.
Yes, when we do internal dosimetry for members of the public, we absolutely build in that age dependency. Yes, our reference individuals are growing. If our reference individual has an intake at age 5 years old, and that radionuclide is long-lived, that reference individual will grow, and as we compute a committed effective dose.
Okay, so any other questions? Please go to the mic. Do you have any?
So that means everybody's like me. Yeah. So if there is no question, then I'd like to thank all the speakers who gave very, very nice talks. And thank you for your attention, and have a good lunch.